Okay, so in a recent class lecture, we were talking about the pieces, major pieces in a computer, and when we were talking about CPU, we went over it fairly quickly. And it's an introduction to logic class, so we didn't get very detailed, but we certainly want to be more detailed than a CPU is a piece that exists. So in the lecture, I drew a quick picture showing the major components and some arrows tracing the data flowing through a CPU, such as the what's in the ALU feeds out to the registers, and the control unit checks that and either feeds it back into the ALU to finish the math, or spits it out to the output if the math part is finished. And just the major components of a CPU and some arrows showing the data flow. And for people that were interested, I referred to the Wikipedia page. There's a picture on there that's been up for 5 or 6 years. So even though I didn't check this morning before shooting this video, after 5 or 6 years, I'm going to assume that picture is still there and just kind of mention it. A couple steps beyond what I drew in class, but still a very crude image that just shows the major components and the flow arrows showing the flow of data through them. And I thought, well, this is a software development class. That's the actual label on it. So why don't we talk about the software a little bit? The protocols for communicating inside of a device are intra-device communication rather than the, say, inter, such as the Arduino device going to the laptop. That's between devices, but inside of a device, we have several different pieces that need to communicate, and we probably don't want to manually write every bit high or low, such as for today's example, got the Arduino controlling things, an Arduino Nano, and I have a micro SD card here. Flip this around to see that. So a micro SD card holding a text file, and then an OLED display to show what's on that text file. And to kind of introduce this, so this is obviously that is a very, very extensive subject. But for a quick introduction, I'm going to show the two that I use most often. Both are two common ones, protocols for communicating between devices built right into an Arduino. So I've been plugged up on the board here, controlling it with the Arduino, and there's a text file on a micro SD card, which we're going to display on this OLED screen for a quick covering, a quick introduction to these communication protocols and kind of a little more in depth of what's going on there than that crude picture that was shown in class, because, well, introduction to logic, all of the IT programs here at the school have to take this course, so some people, that might be important for some people, or maybe it just follows your interest. So let's go over the board and talk about the protocols, and then we'll come back over here and see them in action on this little setup for today. Okay, so just very briefly introducing a couple of the protocols for this. It is a huge field. This is a particular load. Obviously, this is a very precise entire field of studying computer science. So we're just going to kind of introduce it here a little bit more than that, but we are in an introduction class, so I'm not going too far. So we're going to look at the two that I use most often. They're also very, very common, very popular protocols to use. So the first one is serial peripheral interface. Serial peripheral interface. And like everything in IT, obviously we don't say that every time. SPI. So, yeah, for the rest of the video, I'm going to say SPI. Really, when you're talking, there's no need to ever say that unless you're like giving a lecture on SPI communication. Okay? Otherwise, we just say SPI. And this other one I'm going to look at today, the name is even better for what's going on here. Inter IC. Inter IC, so between integrated circuits. And we read that or say that as I squared C. I squared C, which obviously, it's IT stuff. You're going to be doing some Googling around it. Just type I2C. You may sometimes hear it called I2C because that's what we type in Google, because this is kind of a pain to type in Google if we need to do some search items on it. So the basic idea of these two communication protocols is for SPI, that is single master and multiple slaves. So one master, one main control, and then a whole bunch of devices being controlled. And I squared C is, the idea is we have multiple masters and multiple slaves. So for I squared C, when we refer to parallel processing, multiple master processors and multiple slave processors. And for serial peripheral interface, SPI, one single master processor and a bunch of slave processors that it's controlling. And that's why these make, I figured these two would make a good example. Different ways to do it. So let's throw up a picture and kind of describe how the connections happen between this one master and multiple slaves, and how, if we have 20 devices, it communicates to the correct one. Same thing over here. If we have 20 different devices connected, how does it know which one to communicate with? So on today's example, both setups kind of have, I'll kind of draw the whole thing, but I'm doing one device with SPI and one with I squared C, but I want to put more than one in the picture, so I'm going to draw it kind of like this. So there's one master device and two slave devices in both setups. So with SPI communication, there are, in both of them, we're talking about a electrical component. So obviously, we have some power. So a 5-volt rail and a ground, 5 volt and a ground that everything needs to connect to, because they're electrical components, we have to power them. But other than that, there are 4 lines that we need to worry about. So the first one comes out of the master, and then all the lines will make all the connections. So it comes out of the master, connects to both slaves. That's going to be MOSI, M-O-S-I. And that stands for master out, slave in. And you can probably guess what the second line is, because we'll need to go the other way from that too, right? We'll need to go master in and slave out. So communication has to go both ways, right? So the MOSI is going from the master to the slave processors, and the MISO is going from the slave processors into the master. Some nice useful names to remember them by. And the third line that connects everything is obviously we have to synchronize this. So we have some sort of clock line. A clock just tying everything together. Again, it'll connect to both devices. And the other one that we have to worry about, along with the 5 volts and ground, is every device also has a chip select. That's the name I like. It's gone through several iterations and changed several times, so you'll see it labeled differently. You might see SS for slave select. Sometimes you'll see SDA because that's actually one for over here. But when they make the device, they don't know how it's going to connect, so they just label the equivalent ones together. We'll talk about that in a minute. I'm going to use chip select for this. So CS. But you might see SS or SDI. Should be SDA. You might see SDO sometimes, but different labels for the ones. These will definitely be MOSI, MISO, and clock, or some version of clock, something that is obviously the clock signal. And so that's the connection between them. And to send the communication or receive the communication, it goes across the entire line. So on this MOSI line, when the main controller, needs to do something on one of the slave processors, it sends out the entire instruction to everything. Everything hears it, but only the device with the chip select set active will respond. So that's how it kind of keeps that straight. The messages go across the entire network of integrated circuits, and whichever one has its chip select active at the time that message goes out is the one that responds. So that's how that's kept straight. And for our other one, we'll kind of have the same setup of devices. I'm just going to label them master and slave, kind of like that again, the way it's set up. For the current example, we don't really have it. We're not doing too much of the multiple. That's in the protocol. So I'll just draw it with one master controller and 2 slave, one master processor and 2 slave processors. So again, it's electrical, so we need this. So we need power bring into it, and I could have drawn that better. I'm going to have to change it up so they won't quite match. So over here we have our voltage coming in. I didn't match that a little. Like I wrote there, the example today is I'm running on 5 volts, but we can use, there's all sorts of different voltages we can use. And in this case, I'm going to put the ground down at the bottom, because I need to make a connection to this, so I don't want to go across it. So, and I don't want to change this now, just in case somebody's watching the videos taking notes. So note that I drew the 5 volt and ground differently there. So in I squared C communication, we'll have 2 lines to worry about. Well, 4 if we count our voltage and ground. But coming from the master to each one of the slaves, our first line is SDA, and that's going to be our serial data line. So we have serial data, and obviously we need a clock to synchronize everything. So all of our data flows both ways down the SDA line, and the clock ties everything, synchronizes everything, so it's all working together. And for this multi-master part, communication has to go in a lot of different ways. So what we do is both of these lines have little resistors on them going to the source voltage, the the voltage coming in. And so that always makes it so that if nothing is sending anything down the line, so if nothing is happening on this line, everything's just kind of floating. There's not a definite high or low coming or going to any of the devices. This makes sure there will always be a high signal. And then as soon as something wants to communicate, the first thing it does is send out a low signal so that whenever the line drops low, everything knows to listen. And this one uses addresses. Address for each device. So we keep a high voltage, we keep a 1 on both our lines, and as soon as something needs to communicate, it sends a 0 down both lines. Then everything knows to listen as soon as it finds a 0. And as soon as the 0 comes down the line, everything listens, and the next thing coming through will be an address. And then the one whose address that is responds. So that's how I2C communication works. Only 2 lines to connect. Makes it super easy for connections, and a lot easier to sit down and solder 2 lines than solder a bunch. Everything's going to connect to that rail however many we have, so connected with 2 lines, multiple master, multiple slaves, or we need 3 lines plus chip select or slave select for each device on the network. Both have their advantages, so it's kind of a choice as to which one to use. But that's the basics of how the communication works. With SPI, the master processor sends out, or whatever the controller is, sends out the instructions across the entire network, and only the thing currently active responds. With I2C, we keep these lines high at all times, so as soon as something wants to communicate, it sends out a 0. So we keep a 1 on the line, and as soon as something wants to communicate, it sends a 0 down the line, and whenever a 0 comes down that line, everything listens, and if it hears its own address, then it's the one that responds. So that's a start, an introduction into these intra-device communication protocols, SPI and I2C. So let's go back over to the circuit and kind of take a look at these in action. Okay, so just a couple quick notes before we look at the code and then see this thing going. First off is the code's going to look a little bit complicated. We're not going over it in detail because Arduino is a microcontroller, so it doesn't have a whole lot of RAM. It's more of a ROM thing. And the libraries I generally would prefer to use with both SD card readers and OLED screens both try to reserve a bunch of RAM so they can do more, especially the graphics on the OLED. And putting them together, the two that I prefer to use want more RAM than an Arduino offers by itself. And while adding more RAM is no problem, and this is a great place to talk about that, because if you just go to the store and grab a RAM chip to add more RAM into your, say, desktop, and for those that have done it, you just take the old one out, plug the new one in, it probably connects through SPI communication. There might be some I2C ones, but most of the ones I'm familiar with, just the RAM connects through SPI communication. So that could have also served as an example for this. It's just hooking a RAM chip up. But I thought that if I put the RAM chip end of the device, that would overcomplicate the circuit, which we're talking about a little bit more, while making the code easier, and we're not really talking about the code. So there's some messy spots in the code, so I just used a more basic library for the OLED screen. Very basic, so all it does is spit data onto the OLED. So in the case of a text file, it just spits it out as one long line. No line breaks. It spit the whole text file out as one long line, scroll to the end, and do that at the computer speeds, so near instantaneous as far as we're concerned looking at it. So that wasn't going to work, so I used a more basic library that would allow me to write my own buffers, and I just wrote a buffer, the smallest possible buffer I needed to get the words on that, looking right on the screen here. So that made the code look more complicated, and then that particular library names everything gives everything the chip name that it's using. So that makes it look even more complicated. So I wanted to express that point. And another one that hasn't really shown up, I'll talk about with Arduino, but a similar thing with the micro SD card here. You've probably seen devices much smaller than this card reader I have here use micro SD cards. And there's a size thing. And I haven't found a place to put it, but it was on my mind, because if we look here, you can see the OLED screen I chose for today. That'd probably be a good size for a watch. So it was on my mind. And these components, when we say Arduino, I should be saying Nano today. I hope I didn't say Arduino in the introduction. When we're talking about an Arduino, we're really talking about this right here. That's a Atmega 328, the chip there. And everything else here is just a PCB to kind of hook up that chip and make it big enough to work with, right? It's a good size to fit in my hands and go in the breadboard to mock up a circuit. So that in the case of say a watch like I was talking about, get this OLED screen and design it up with the SD card reader that's a nice size to work with the hands when prototyping things. Same thing with a microcontroller that's a good size to work with our hands when testing stuff. And when the design works, then just order this, the small pieces from a factory in China without all the extra stuff. So remember, these are just pieces. So when you see these, it's really this chip, the Atmega 328. And then the rest of this is just a pre-connected version to make it easier to work with when we mock up designs. And a whole lot of the components you'll see in these videos are like that. It was just on my mind because every time I look at the OLED screen, I think of that, or it often makes me think of a watch size. But those are the two main points, and I guess the main takeaway from those would be the RAM. We're talking about it. One of our things is talking about SPI communication, and when you go put a RAM chip in a new RAM chip in your desktop or something, you're probably using SPI communication to connect that. Just to let you see where this applies to the computers you're familiar with. Okay, so just a couple things to glance at in the code here. Like I mentioned, these are standard protocols, so there's already libraries pre-built ready to go for it. So just bringing in the C++ library that has the standard SPI communication protocol set up for the Arduino, and same thing with the C++ library that has the standard I2C set up for the Arduino, kind of built into the chip. Since that point I made earlier about it being big enough to work with, there's plenty of room, so they went ahead and wired up some pins for those. Went ahead and wired up those standard protocols, or some standard protocols. Then, and for today's example, just bringing in some libraries. So a library that has all the functions to read and write to an SD card. Then this is the super stripped down basic library that just takes 8 by 8-bit blocks to display on this chip, the SSD 1306 chip. That's the controller chip for an OLED screen. Initialize everything. Just set up some basic error handling, like if not SD begin. So if the SD card didn't initialize correctly, that's the negation here. If it doesn't initialize correctly, throw up an error message. Same thing on this other one. If it call the initialize method, if it triggers true for the negation of initializing it, then throw up an error message. And then just a file to, then just a method to read what's on the file, which obviously we're not using this language in core in the class, so, but some of the concepts might look familiar. So a string to put things into, then we create a file handler that looks at the file, then we take whatever the file handler sees and puts that in the string. And then the rest of this is just kind of a super basic buffer, because this had to use the strip down library, so it just feeds the data straight through and would give one long line with no line breaks or no word wrapping or anything, and pretty much immediately scroll to the end of the line. So this is just the minimum necessary buffer to fill up the screen with words. But the main point here is these are pre-built communication protocol standards. So all we have to do is ask for them, and then they're ready to go. So let's go see the circuit in action now. Okay, so like I said, the Atmega 328 put onto a PCB big enough to work with leaves us plenty of room to do some extra stuff too, such as hook up I2C. By default, it goes to analog pins 4 and 5, and the SPI goes to pins 11, 12, and 13 for the MOSI, MISO, and clock. And then you just choose any pin you want, other pins for chip select, or some other way to power the chip select. And this is a typical setup I have to work with these. Most breadboards typically have little knobs on one side and holes on the other, so they link together and get a nice big spot to work with, and more of these rails or buses going down the side. So up here, got power and ground, lots of places to get power to things. And then down the middle here, where the connection made a lot of buses, I usually is where I always keep the SPI communication, so that I have a MOSI rail, a MISO rail, and a clock rail, and then I can hook up lots of SPI devices. Lots and lots of places to hook those up. And same thing down here, have the which order they hooked up in. So the SDA, the clock, and then the SDA rail, so I can hook up lots of I2C devices. And plenty of room to work with and stuff, and it's coming default out of there. So when I apply power to this circuit now, we should see this light up and activate. Alright, so our Arduino is booting up. So it reads the text file off the micro SD card with SPI communication, spits those words back on the screen with I2C communication, and it looks like I got the video out of phase. That bar's not showing up when looking at it. It's, video is flashes of pictures, and the way screens work, it flashes. It's called multiplexing. Maybe I'll do a video on multiplexing about how it's doing, but it flashes through the rows really, really quicker than our eyes can see, but every once in a while it synchronizes with the video, so that, like that. The video does catch them being off. But you can see it working. That's kind of how the components inside a device communicate with each other. Just a basic start there, obviously. It gets a lot more in depth, and those are not the only protocols we have to work with this. There's lots and lots of that. It's a huge field. intra-device communication. But those are a couple basic ones, seemed a good starting point. And I wanted to be a little more in depth than that picture in the lecture, which was just the components with arrows going between them, and kind of talk about how a little more detail about how some of this works for those who are interested in it or going somewhere into that aspect of IT.